All right, sorry. So coming back to the example, so how do we factor, how do we find this p? Well, we can simply use the theorem of Dedekind. We know that r is really z square root of 23, because 23 is congruent to 3 mod 4. So we simply can look at what happens to fx, which is x squared minus 23 modulo 2. Well, it becomes a square, right? And so it's you write the prime, which is 2, and then you take a polynomial that becomes congruent to a given polynomial. So what do I want to say? So let's do this step by step, okay, so that everything is clear. So first you take this polynomial. Suppose I want to find out how 2 factors. So I take x squared minus 23 and I compute modulo 2. Well, this is x squared plus 1, yeah, mod 2, and this is the same as x plus 1 squared. Alright, so this is mod 2. Okay, then the theorem tells me that this p is 2, and then I have to take this polynomial and plug into it this 23, square root of 23. So it is 1 plus square root of 23, and also because this polynomial becomes a square, it means that 2 is p squared. Alright, so this is my p. Great. And then I have to factor 3. Well, 3 does not divide the discriminant. So to figure out what happens to 3, I simply take the same polynomial and see if it factors into 2 primes, into 2 distinct linear factors, or if this still remains irreducible. So x squared minus 23, this is congruent to well, x squared minus 2 mod 3. And this polynomial, well, this polynomial is irreducible because 2 is not a square modulo 3. Alright, so 3 is prime. And because it's prime, its norm actually will be 9. So we can immediately exclude this. The norm of p is 2. So, well, what does the theorem tell us? The theorem tells us that every ideal class contains an ideal whose norm is less or equal, what was the bound, than 4. Okay, and so what are the possibilities? This is the generator. Okay, the 3 does not, the primes, there are no primes that divide 3 and have norm less than 4. So what can happen? Well, what can happen is that I have this p, and I have p squared, which is norm 4, right? So this also can be one of the ideal classes, and I can't have more because 1p, this exhausts all possible ideals whose norm is less than 4. So either it is possible that this is 1. Okay, so it is either Z3 or Z2 or it is the trivial group. We have to figure out what it is. But just from this information, I can give you an explicit bound on the class number, which is pretty. It's not a bad bound. We will see that we're definitely off by more than 2 because the class group turns out to be trivial. But at least you know that it's a cyclic group and its order is at most 3. Right, so why is this? Why the class group is trivial? Well, it depends on the observation that this P is actually principal. So how do you see this? You see this by observing that this is also equal to this ideal, right? All I did, I added 4 to this number, and if I subtract 4, which is in the same ideal from this element, I will get this element. So definitely these two ideals are the same. Now, on the other hand, this 5 plus square root of 23, if I multiply this by its conjugate, I get 5 minus 23, which is, well, 25 minus 23, and this is 2. Okay, so this means that this element divides 2. So this already contains 2, namely I can take this element of the ring and multiply 5 plus square root of 23 by this element, and I will get 2. So 2 is redundant, which means that my ideal P is generated by this element, so it is principal, which means that the class group is trivial. Alright, so this ring is a principal ideal domain. It's not quite obvious that this is a Euclidean domain, but I think it is also a Euclidean domain. Alright, you might be asking, well, where are the non-trivial examples? We know one example where the numbering is not a PID, and this is the most famous example that is usually given, and this is R equals Z square root of minus 5. And so this is not a PID. Okay, so again, in this case, the discriminant of R is 4 times 5. So the absolute value is 4 times 5, because minus 5 is congruent to 3 mod 4. Okay, and this is indeed the full ring of integers. And the Minkowski bound M gives me, so now S is 1 because this is a complex number. This is 4 over pi, and then I have 2 over 4 square root of 4 times 5. Okay, so this is 4 over pi square root of 5. Okay, and this gives me approximately 2.8. Okay, with 2.8, I have to just concentrate on primes whose norm is 2. So I have to factor 2. into prime ideals, and 2 again ramifies. You can repeat the same argument as before, and you get that 2, 1 plus root of minus 5 squared. So this is the prime decomposition of 2, and the norm of this prime ideal is indeed 2. And we also know that this ideal is not principal. Okay, this we proved. You can try to reprove this on your own, which is a useful exercise. But since this is not principal, and this is a generator, right? Well, what do we have? We have, so p squared is 1. Actually, the same applies, to the previous example. What I said was kind of silly, because there we have 2 equal to some p squared, right? Which gives you the same relationship. So the class group in the previous example, just from the fact that the only primes I have to consider are the primes that divide 2, or the p in the prime decomposition of 2, implies that the class group is either trivial or it's cyclical for the 2. So in this case, again, I come to the same conclusion, so it's either trivial or it's cyclical for the 2. Since this ideal actually is not principal, so since p is not 1, we get that the class group of R is Z2. Alright, so this is very nice, because now we have more information about the ideals. We knew that this is not a principal ideal domain, but now we know how far it is from being a principal ideal domain. Well, it's not very far, it's just slightly off, and this ideal generates, in some sense, every other up to this equivalence, it generates every other non-principal ideal, right? In the previous example, we had p equal 1, because p was principal, so then, of course, 1 squared is still 1. All right. So this is another example, and then let's do one more example, which is more complicated. So what example should we do? The example is again a quadratic extension, but square root of minus 14. Actually, before I do this example, let's take a break, because it's easier to upload shorter videos.